the sum and difference formulas. Right, we're going to start out looking at sum and difference formulas for the sine function. Sine of a plus b or sine of a minus b. Notice that the formulas look almost the same. Sine a cosine b to start it out, cosine a sine b to end the formulas. It is the plus or the minus sign in the middle that makes these differ. When we're doing the sum of angles, it's a plus. The difference of angles, it's a minus. And so we'll use one of these formulas to answer this question. Find the exact value of the sine of 75 degrees. Now, an exact value is not something you can find using, say, the TI-83 calculator, but we can find it by using the formula here. Now, here's how you first have to look at this. 75 degrees is not one of the angles that you find on your unit circle. Think about starting out quadrant 1 of the unit circle. You've got 30 degrees, 45 degrees, 60 degrees, then 90 degrees. Well, all you have to do is look at these and examine them and see if we could either add or subtract 2 of them to get 75. And I'm sure you noticed that 30 plus 45 would give you 75. So therefore, we will use the first of these 2 formulas here, sine of a plus b. So let's go and let's write that out. All right, so we're doing the sine of 30 degrees plus 45 degrees. That's how we're getting this sine of 75. And according to the first formula, it will be the sine of the first angle 30 degrees times the cosine of the second 45 plus the cosine of the first 30 degrees times the sine of the second 45. Now at this point, we'd have to refer to our unit circle values. This is why I always encourage students to have them memorized. The sine of 30 degrees is 1/2. And then the cosine of 45 degrees is square root of 2 over 2. All right, then we have our plus sign, and now we're going to do the second half of the formula. The cosine of 30 degrees is the square root of 3 over 2. That's times the sine of 45, which is square root of 2 over 2. So let's see what this will give us. The first fraction, when multiplied, gives the square root of 2 over 4. The next one gives the square root of 6 over 4. With radicals, you multiply the radicand, that is the part underneath. And finally, we can combine these since they have a common denominator of 4. The numerator would be square root of 2 plus square root of 6. And that would be the exact value for the sine of 75. Please notice, common mistake students make is they try to add the 2 and the 6. No, you can't add the radicands. Now we have a sum and difference formulas for cosine. And notice here that the beginning part is the same in both of these as is the ending part. It is in fact only the minus or the plus sign that changes in the 2 of those. As this example says, let's find the exact value of the cosine of 15 degrees. Well, 15 degrees is not one of those standard angles within our unit circle, so let's list a few of the standard angles. Starting out in quadrant 1, we have 30 degrees, we have 45, we have 60, but you hopefully have already noticed that I could subtract these 2 angles in order to get 15 degrees. 45 degrees minus 30 degrees will equal the desired 15 degrees. So let's select the proper formula and work this example. The problem that we need to work is the cosine of 45 degrees minus 30 degrees, which of course it will then give us a cosine of 15. Well, notice that's a subtraction, so it is a second of these formulas which we would select there. And so that second formula says it would be the cosine of the first of those angles times the cosine of the second of those angles. Then it is a plus sign, and then it is, notice, the sine of each angle multiplied. So the sine of 45 degrees times the cosine of 30 degrees. And of course, knowledge of the unit circle is indispensable. Here again, that first cosine is the square root of 2 over 2, and the second one is the square root of 3 over 2. Over here to the right, the sine of 45 is square root of 2 over 2, and the cosine of 30 is just equal to 1/2. Well, let's multiply these. When we do the first, square root of 2 times square root of 3 is square root of 6. It's over 4. And the second one, it's just square root of 2 over 4. And we get the square root of 6 plus the square root of 2 all over 4. All right. Oh, you know, something that just occurs to me and may have occurred to you, the listener. We also could have used the 45 and the 60 there to have obtained the 15. See, we could have done 60 minus 45 to achieve our desired 15-degree angle. Obviously, the work would look a little different, but the same answer would come out in the end. Finally, we'll look at sum and difference formulas for tangent. Notice these are both fractional in form. At a glance, they look very similar to each other, but of course the addition and subtraction signs are opposites of one another. All right, so here, I figured let's do a problem where the angles are given in radians. So let's find the exact value of the tangent of pi over 6 plus pi over 4. We're adding there, and so in this case, it will be the first of the two formulas that we'll want to use. So let's go and write that one out. The tangent of pi over 6 plus pi over 4 will be, according to this first formula, the tangent of pi over 6 plus the tangent of pi over 4 over 1 minus the product of those two tangents there. 1 minus tangent of pi over 6, tangent of pi over 4. Now, even though you know your unit circle, the tangents aren't quite as quick to read off, because the tangent on the unit circle, it's a y value over the x value. So I'd like to do a little sketch over here, over on the left-hand side, just to help us organize our thoughts a bit. Certainly to help me organize mine. We have pi over 4. We know that that's the same as a 45-degree angle. Okay, my picture's not perfect there, but you know what I mean. Pi over 4, recall that the coordinates at pi over 4 are square root of 2 over 2 and square root of 2 over 2. Now the tangent at pi over 4 would equal the y value over the x value. Well, since they're identical to each other, that tangent would just equal 1. Let's now go and obtain the tangent of pi over 6. Once we do that, we can go continue with our problem. So for pi over 6, recall that the coordinates on the unit circle are square root of 3 over 2 and 1/2. So let's see what the tangent of pi over 6 is. It would be the y value, 1/2, over the x value, square root of 3 over 2. Looks like our work off to the side will probably be more work than we'll do on the problem itself. We'll have 1/2 times the reciprocal of the lower fraction, 2 over square root of 3 there, and that equals 1 over square root of 3. We could rationalize that denominator, but I'm just going to plug it into the formula, and then we'll see what happens when we do that. So I'll come back over here. and I'll just take the time to plug these values in. So I'm looking at this formula here and plugging in the values we've obtained. Tangent of pi over 6 is 1 over square root of 3. And then the tangent of pi over 4 is 1. Underneath we have 1 minus the tangent of pi over 6, which is 1 over square root of 3, times the tangent of pi over 4, which is equal to 1. All right, that's what we have. We have 1 over square root of 3 plus 1 over 1 minus 1 over the square root of 3. That fraction is what we call a complex fraction. It's a fraction made up of fractions, and it's always desirable to try to change it out of that form. We can do it without too much trouble here. Notice that it's the square root of 3 that we really need to eliminate. So let's multiply the top of this fraction here by the square root of 3, and then we'll do the same thing down here. Now when you do the square root of 3 times 1 over the square root of 3, you get 1. And when you do the square root of 3 times 1, you get square root of 3. Similarly on the bottom, square root of 3 times 1 is square root of 3. And then when you go over the minus sign and multiply, you will just get 1. We no longer have a complex fraction. It would be optional to rationalize the denominator, but I'm going to leave this answer as it stands. All right, folks. Wish you all good luck.